Hi everyone. Today we're going to talk a little bit about light and energy. Light is a non-mechanical wave, which means that it is a wave that does not require the presence of matter in order to move. This would be the opposite of something like sound, which is a mechanical wave. Sound can only move if there is matter present. Since light is a wave, it will have all the properties of a wave. It will have a wavelength, a frequency, a period, a speed, and an amplitude. It will also carry energy. As you can see here in the image shown, there are many different kinds of light on the entire electromagnetic spectrum. Some light is visible. That is the visible light spectrum, ranging from around 400 to about 750 nanometers in length. You'll notice on this graph that the visible light spectrum is a very, very small fraction of all possible light. There are many other kinds of light, including X-ray, ultraviolet, infrared, and even microwaves, which are not demonstrated here. That would be in between infrared and radio. So let's talk about wavelength and frequency, as these are the two most common properties that we want to know for a wave. A wavelength is the distance from one wavefront to the adjacent wavefront. Usually, this is measured from one peak to the next because that is the easiest way to measure it. Units for wavelength would be meters or nanometers, micrometers, centimeters, some length unit, preferably one of the ones that is connected to meters as opposed to using feet or inches, although those would technically be acceptable. Frequency is the measure of the number of waves that pass by in a given time interval. Usually the time interval studied for frequency is 1 second, but sometimes you could do it for a minute or an hour depending upon what you were specifically looking at for waves. The units for frequency are therefore a time inverse. So for example, if we're going with the usual seconds, it would be seconds inverse, or seconds to the -1. A second inverse is also equal to hertz, 1 hertz, which you will occasionally see instead of using the seconds inverse. They are the same thing though. Light and wavelength and frequency have an indirect relationship, or inverse relationship. That is to say, as one of them grows, the other one must get smaller. This makes sense. The longer a wave is, the longer it'll take for it to pass by, and so the less of them can pass by in a second. So a long wavelength implies a shorter frequency. Conversely, if I have a short wavelength, that implies I can get a lot more waves through in a second, and therefore a short wavelength implies a much higher frequency. The formula that connects wavelength and frequency is shown here. C equals lambda nu, where C stands in for the speed of light. Speed of light is 2.99 times 10 to the 8th meters per second. Lambda, which is the upside down Y character, stands in for wavelength, and nu, which looks just kind of like a fancy V, is frequency. Again, wavelength should probably be in meters, since that is the length unit that is part of the speed given, and frequency would be in seconds inverse or hertz. We can also measure the energy of light because all waves carry energy. Sound waves carry energy, ocean waves carry energy, and light waves also carry energy. The energy of a wave, including a light wave, will be dependent upon the frequency. How often you're confronted with a wave is going to be directly proportional to its energy. For light, formula for energy of a packet or photon of light is E equals h nu, where E stands for energy measured in joules, the accepted energy unit, and h is a constant known as Planck's constant. It was an experimentally determined constant during the early phases of the development of quantum mechanics. Planck's constant is equal to 6.626 times 10 to the -34th joule seconds. Units for this are joules times seconds. And nu, as we have seen before, is equal to the frequency.